This video is on colligative properties. So colligative properties are properties of a solution that depend only on the number and not the identity of the solute particles. Some examples of colligative properties include vapor pressure lowering, boiling point elevation, and freezing point depression. So in vapor pressure lowering, a non-volatile solute lowers the vapor pressure of a solution simply because they get in the way of the solvent particles entering the vapor phase. So we can see this in the illustration here. I have a pure solvent, and my pure solvent can easily jump out of the liquid phase into the vapor phase. Here I only have solvent particles. However, in my solution, where I have a solute dissolved in my solvent particles get in the way of my solvent particles coming into the vapor phase, thus prohibiting that from happening. Therefore, the vapor pressure inside my container of my solution is less than the vapor pressure of my pure solvent. The boiling point of my solution is also changed. A solution requires a higher temperature to reach the same vapor pressure as a pure solvent. Thus, the boiling point increases. Again, in order to get my molecules into the vapor phase, more energy is going to be required. Thus, a higher boiling temperature is needed to achieve the same sort of vapor pressure as I have in a pure solvent as I do in a solution. We call normal boiling point the temperature at which the vapor pressure equals 760 torr. We know this is also equal to 1 atmosphere. Freezing point can also be changed, and this is called freezing point depression. Here, lowering of the vapor pressure of water lowers the freezing point. The solute gets in the way, and the solution is more difficult to freeze. So if we were to look again at our example here, if I have my pure solvent, when I lower the temperature, my molecules move slower and slower, and eventually they go through their phase change and they become a solid, and they get into a uniform position. When a solute is added to my solvent, now my solute particles are in the way of my solvent particles from freezing or coming together in a unified fashion. Therefore, they must get to a lower energy phase or a lower energy state to push out our solute particles so that way our solvent particles can freeze, or they can get to a low enough state where they don't mind having the solute particle next to the solvent particle. So this is why we put salt on the roads during the winter time here. The salt mixes in with the precipitation falling, usually snow, and then when friction from our car tires runs across us, that temporarily melts the snow in addition to the pressure that it puts on it. And that is going to allow the salt to dissolve into the water, and therefore the salt molecules will get in the way, or the salt ions will get in the way of the water molecules from freezing, and it'll have to get to a lower temperature before the water refreezes on the roads. We can determine actual changes in boiling point and changes in freezing point using our colligative property equation. Here, my change in temperature of the boiling point, my little b, or my change in temperature of my freezing point, is equal to I, which is my Van Hoff factor, times Kb, or Kf, which is your constant specific to the solvent. In our cases, we'll just look at water. And then M, which is our molality of our solute. Remember that molality of solute is our moles of solute per kilogram of solvent. Okay. So here we have our increase in boiling point because we have boiling point elevation. We have a change in temperature here, which is freezing point depression. Which is a decrease in freezing point. I is the Van Hoff factor, and this is the number of particles that have been dissolved. So if I were to look at sugar, this is a molecular formula, or covalent formula, it doesn't break down into individual parts, it just breaks down into individual molecules, and this is one molecule. As opposed to an ionic compound, in water, this ionic compound would break apart into the sodium ions and the chloride ions. So I break into sodium ions and chloride ions, and I have one of each in each of my compounds, so it'll give me an I of 2. If I had calcium chloride, that breaks down into calcium ions, and it breaks down into 2 chloride ions, so it gives me a total of 3 ions that it breaks down into, so my I would be 3. My constant specific to the solvent, we're going to use water for almost all of our equations, unless it tells you otherwise, and then you'd get the other constants. And that's going to be 0.51 kilogram degrees Celsius per mole for boiling, and for freezing, 1.86 kilograms degrees Celsius per mole. So let's go ahead and go through an example to put this into practice. So I want to know if a solution is made by 100 grams of sodium chloride in enough water to make 1 liter of solution. It has a density of 1.05 grams per milliliter. I want to therefore calculate the freezing point of the solution. So given to me in my equation, I have my mass of my salt, my volume of my solution, and my density of the solution. I want to calculate my change in freezing point, and I know that change in freezing point is equal to my Van Hoff factor times my constant for water times my molality of my solute, in this case sodium chloride. First, to find my Van Hoff factor, I know that sodium chloride is ionic and breaks down into a sodium and chloride ion. That makes 2 total ions for each one of my compounds, and so it gives me an I value equal to 2. I know my Kf, it was given to me above, is the 1.86 kilograms degrees Celsius per mole. And now I need to calculate my molality. Molality is moles of solute per kilograms of solvent. My solute being my sodium chloride, my solvent being my water. I can convert my grams of sodium chloride into moles of sodium chloride using molar mass, and I get 1.71 moles of sodium chloride. I then need my kilograms of solvent, and that is where my density is going to come into play and my total volume of my solution. So I know that 1 liter of solution is equal to 1,000 milliliters. For my 1,000 milliliters of solution, I can use the density to figure out my total number of grams of my solution. So I have 1,050 grams of my solution. If I have 1,050 grams of solution, and 100 of those grams were my sodium chloride, that means that the other 950 grams had to come from my water. Looking at molality, I need this to be in kilograms, so converting 950 grams to kilograms, I get 0.95 kilograms. Plugging in to find molality, I take my moles of sodium chloride divided by my kilograms of water, and I get 1.8 molal for my sodium chloride. Now I have all my parts, my I, my Kf, and my M, to then plug in for my equation. So my change in freezing point is equal to 2 times 1.86 times 1.8 molal, which is moles per kilogram, and that gives me 6.7 degrees Celsius. I know that water freezes at 0 degrees Celsius, and I'm lowering the freezing point. So 0 minus 6.7 degrees Celsius gives me a new freezing point of negative 6.7 degrees Celsius.